In this challenge review, we're going to solve the moss giant movement. So let's look at our pseudocode here and start filling it in. If the current pose is point A, then we're going to move to point B. So here, we're going to say if current pose, which is our transform.position. So if transform.position is equal to point A dot position, then that means that we're at the start and we need to basically move to point B. So we're going to say transform.position is going to equal vector3.move towards, and we're going to move towards from our current, which is transform.position, to the target, which at this point would be point B.position. And we're going to move at the speed of whatever our speed is set to in the inspector. So here we're going to say speed times time.delta time. Let's save this, and we can continue filling in the rest. Move to point B, and likewise we're going to say else if current pose, which is the end, so transform.position equals point B, that means we now need to switch, we need to go back. So if transform.position equals point B, then what do we need to do? Move to point A. So we're going to say transform.position equals vector3.move towards, and if we read the tooltip, current to target. So we're going to take our transform.position, and we're going to move to point A dot position. From there, we're going to say speed times time.delta time. Let's save this. And this needs to be point B dot position. If we save this and head back into Unity, let's go ahead and test this out. Now, if you're already foreshadowing ahead, you should see why this isn't going to work. Let's go ahead and run this, and let's see what happens. Right now, we know we're on point A for the moss giant, which is 6.53, and let's see if we move. All right, so we are not moving. The question here is why not? Why would we not be moving? So if we look at our code here, what's happening? If transform.position equals point A, and else if transform.position equals point B. To debug this, first off, we want to make sure that at least one of these statements is true. Let's add a debug.log, and we're going to say point A, and here we're going to say debug.log point B. Let's save this. Let's head back into Unity. And let's rerun this. So here, you can see here that point A is being called. Now, point A is being called repeatedly, but not actually moving us. Why not? Why would it not be moving us? Well, the reason why it's not going to move us is because vector3.move towards, our speed is most likely set to 0 in the inspector. And if we check here, it most certainly is. So here you can see that our speed is set to 0. And if we change that to say 1, let's hit enter to save that value, save the scene. Let's run it again. And this actually still isn't going to work. And the reason for this is going to be very obvious once we see what happens. Now, point A got called in the console here. You can see point A was called one time, and then it stopped. What happened? Well, point A is at 6.53, and if we look at our moss giant, his position is now 6.55. He moved a little bit. The issue here is our update method. What we've done here is we're checking if transform.position equals point A. Well, it did. But what happens as soon as we move towards our target? This is no longer a true condition. This update method is running 60 frames per second, which means that within the first frame, we already have a false condition, and now we're stuck. That means that we need a variable that's going to control this logic to say, hey, continue on forever until you reach the end. So to do this, we're going to have a bool called switching. So we're going to say here, private bool, and we'll say underscore switch. So private bool underscore switch. And here, we're going to make sure by default it's going to be false. And then in update, what we're going to do is if transform.position equals point A.position, we can simply say switch equals false. And then here, if we've made it to point B, we need to turn around. So we're going to say switch is going to equal true. Now that we have that, we can create another if statement down here that's going to check for this logic. So if switch equals false, then what do we need to do? Move right. Else if switch is equal to true, what needs to happen? Else if switch is equal to true, we need to move left and come back to point A. With that logic, we can now take the movement code and we can place it in here. So if switch equals false, we're going to move right. And we'll straighten this up. And it looks like we have a typo here. Switch equals false. Okay, so if switch equals false, we're going to move right. So we're going to take our current position, move to point B. Else if the switch is true, what needs to happen? We're going to move left. So we're going to take this movement code and place it here. All right, let's save this. And now we can test this out and we should have a functioning waypoint system. The next thing I want to show you guys is how we can optimize this even more. Because right now it's not very optimized, but there is something we can do. Let's save this. Let's run the game. And as you can see here, our player is now moving to the exact waypoints. And when he gets to the end, he's gonna turn around and come back. And just like that. So one of the things you'll notice that we have to do is we have to flip him. We'll get to that in a later challenge. But as you can see here, we have a functioning waypoint system. He moves back and forth just like we want him to. Let's go ahead and optimize this code a bit. So currently in our code, we have 4 if statements that are required to get this done. Now there is a better way we can do this where we can literally eliminate this switch variable and these 2 if-else statements in general. We can just get rid of them and just have the functioning code of this. And I'm going to demonstrate how to do that. However, if you do like this implementation and it helps you understand it, then what I encourage you to do is keep it. And what we can do is we can just clean this up. So here we can create a new function called void, we'll say void movement. And let's take the code inside of our update method, copy it, and let's paste it inside of movement. From there, inside our void update, we'll call the movement method. Let's save it, and everything is good to go. Now, inside our movement code, if you're interested in optimizing this even further, one of the things we can do here is we can actually delete the switch code here. Now, the reason for that, the only reason why we require this is because our system isn't modular. It is hard-coded to say go to point B and hard-coded to say go to point A. What if we made it to where this was a generic variable, such as just a target, and we reassigned target? That would make it to where we no longer had to use move towards in 2 different if statements. We can just use one. To demonstrate what I'm talking about, we're going to remove the switch code. We're also going to remove the switch bool up here. Instead, what we're going to do is we're going to create a vector3 variable to store the current target. So here, vector3, and we'll say current target. Once we've done that, we can then hop into our code here and rewrite the logic. If transform.position equals point A.position, what's the target? The target is going to be B, right? So here we can say current target equals point B.position. Else if transform.position equals point B.position, we could say current target equals point A. And just like this. Current target equals point A dot position. Now, alternatively, we could just use an else statement and just have the else statement say this. The reason for that, though, is if you wanted to add a 3rd waypoint later, you wouldn't be able to. So we want to make sure that it's an if-else if. So here, transform.position equals point A, we say current target is point B. If the transform.position is point B, then current target is now point A. Now that we have that if-else logic, we can simply just come down here and update and say transform.position is going to equal vector3.move towards, and it's always going to take our transform.position and move it to whatever the target is. So we're going to say current target. And we'll go ahead and give it a speed of whatever our parent object says our speed is, times time.delta time. You can see here that it is much cleaner, much easier to read in my opinion, and if we save this and head back into Unity, we should have the exact same result. Go ahead and run this. And as you can see, we're moving to point B, our enemy moss giant. And once he gets to point B, he should return. And he does. So there you go. That is the enemy AI movement. In the next video, we're going to continue polishing this up.